Now, for part B, we want to know the tension of the rope just before the collision with the object. So we're still before the collision. I've used conservation of energy, so let's actually draw a free body diagram of M2. So I'm going to have the tension going up, and I have the weight onto due to the earth. And so what's actually happening here is that this rope makes this person move in a circle. Sorry, so the force is not acting on the rock, it's acting on the person. So anyway, the person's swinging in a circle because of the tension of the rope. So the way we set up that force equation is the sum of the forces equals ma. The a we're talking about is centripetal acceleration. So we're going to have t minus m1g equals m times v before we hit the rock squared, divided by the radius, which is L. And so we're going to have t minus m1g equals m times 2gl, m1 times 2gl, divided by L. And so our tension actually works out to be 3 times m1 times g for part B. Yay! All right. Now for part C, it says what is the speed of the object and the person just after the collision? All right, now we're going to use conservation of momentum. So we're going to have m1 v before equals m1 plus m2 times v combined, which I'll call v after. So I'm going to end up actually getting that m1 over m1 plus m2 times the square root of 2gl equals v after. Excellent. So that is part C. Now we want to know some ratios of this whole system before and after the collision. So let's go ahead and see if we can do that. So first, let's get the kinetic energy before. Well, there's only the person moving, so their kinetic energy is going to be 1/2 m1 times v before squared, which is going to work out to 1/2 times m1 times 2gl, because that's vb squared. And so I'm getting ke before simply equals m1 times g times L. Great. Now let's go ahead and get the kinetic energy after they collide. This is going to be a little trickier because we have this whole messy expression. So the kinetic energy after is going to work out to be 1/2 times m1 plus m2 times, here we go, m1 squared over m1 plus m2 squared times 2gl. That's pretty complicated to get this before to after ratio. So what I'm going to do is I'm going to actually take these guys and put them on the next page, and we're going to do a little work with these on another sheet. This is going to be one of the longer videos. I'm pretty excited about that. Yes. All right. Let's put these up here, because they're going to want us to actually simplify this guy. So here we go. I'm going to simplify this kinetic energy after. So first, I know that this cancels. Excellent. One of them cancels. And so I know the 2 cancels. And let's see if we can find some kind of common denominator. So ke before. Let me go ahead and write that also as m1 plus m2 over m1 plus m2 times m1 gl. And so what I'm ending up getting here is that the ke before over the ke after, and let me make absolutely sure that I have this right. Yes, we want the kinetic energy before ratioed with the kinetic energy after. So here we go. This is going to be a little annoying. So I'm going to end up getting m1 plus m2 times m1 gl divided by m1 squared gl. So I did have a reason for canceling the m1 plus m2 in the denominator, which I'll leave you to figure out. And so it looks like one of the m1s cancels out, and the g and the l's cancel out, and I'm left with m1 plus m2 over m1 is my ratio of energies. That is a great place to stop before doing the very last part, which is part